Hey, what's up, guys? Brother Q, and today we're going to be discussing bridges. I'm not going to go down to the hundreds or how many different types of bridges, but we're going to be discussing the typical bridge you see in your neighborhood, and that's more than likely a truss bridge. A bridge is any device or structure that allows you to cross from one thing to another. The different types of bridges are pretty much used based off of how you want to handle the loads. And that is a key word that we talk about with bridges and in physics, load. Load is the capacity of that something can handle or can bear, you know. And so when we talk about bridge, we're really specifically thinking about how much weight can this handle. Weight, mass times acceleration, you know, is what this bridge is all about, being able to handle a specific load. The ability to handle a load is based off of how the bridge is structured. And so ultimately when we make a bridge, we're actually creating a structure that is able to manipulate the forces associated with the objects that are crossing, that are crossing it. Now, a truss is a specific type of geometric shape that we use in engineering, and you can find trusses everywhere. We're going to highlight them in bridges, but they're used in cranes, dollies, like towers, just everywhere. I think they're even used on the arms of the ISS space station or something like that. Yeah, they're really cool ways of handling structural loads. Why do we use truss bridges in engineering? Well, intuitively, most people would think that they would make a square or a rectangle or something like a box to hold up a big structure. And the reason why we don't want to do that is because structures shaped as squares or rectangles typically allow the force that's being applied to the top of them to deform the shape of it, and it winds up creating like a parallelogram or a rhombus as it rotates the pressure, the force that's being applied to the top of it. And so we don't want that, because that's what's going to end up in catastrophic failure. What we want is to be able to control the way the force is actually being distributed through the legs of whatever structure we're working with. With a triangle, the weight that is added or put on top of a triangle is added to the joint. Why is this so important? The joint, right, is distributing the weight that it has to bear to the legs, to the members. Whereas in a square, not only is it putting the weight on the leg itself, which is actually putting a tension on the end points of it, it's now also forcing the dynamics of the structure itself to be taken into consideration. Like, what is it made out of? Can it handle that much load? And this has nothing to do with the way it's designed. It's just the dynamics of the material itself. With the triangle, though, the load is distributed through the members by meeting at the endpoints. Engineers love triangles. More triangles. More. So a typical truss bridge is comprised of an abutment which holds this structure to whichever, to the ends of it, the bottom chord, which we say the floor or the deck, and the top chord. And now the legs, which makes up the walls, and which you have your bottom chord, top chord. These positions here would be your abutments, which affix it to the areas in which that you're trying to connect. These are your chords, these are your joints, and these are the legs, pillars, whatever, so on and so forth. Truss bridges are categorized by how they're oriented. So if you can drive through it, that's a through truss bridge. If you can drive on it, that is a deck truss bridge. And if there's no ceiling, pretty much, that's a half through bridge. Very simple. All right, there's like over 30 different truss bridges. I'm not gonna discuss all of them. In this video, I'm probably gonna discuss the Warren Bridge, Pratt Truss Bridge, the Howe Truss Bridge, and whatever other one that's somewhere in these links that you can just hit. A Warren Truss Bridge consists of equal triangles, very easy to identify. Equilateral triangles throughout the entire bridge, very easy to identify, very cool to make, very simple to make. And the forces, of course, the weight that it has to load, the forces are distributed amongst all of the different triangles individually. Pratt Truss bridges are designed to direct the forces that it has to bear towards the center of the bridge. Opposite the Pratt Truss Bridge is the Howe Truss Bridge, which pretty much does the complete opposite of the Pratt Truss Bridge, in which the forces are directed outward. Now, when analyzing your bridge, you want to take in consideration which part of your bridge the members in the joints are actually experiencing compression and which parts are experiencing tension. Now, there's different ways of doing that. You have method of members, method of joints. I'm not going to go into detail in that here, but typically most people go down the method of joints. And so pretty much you just want to remember that. How your bridge is designed to handle the compression and tension forces. That's the beauty of being an engineer. Now, with your bridge, the joints are going to be held together by glue. But in a real truss bridge, they'll be held together by something called a gusset plate. And that was going to be used to hold the pin. Now, ours are fixed, but in a real truss bridge, there would actually be a pin inside of the joint that allows these members or legs, whatever, to move slightly. And the gusset plate will be used to lock the members into their position. Another thing to remember with truss bridges, the load is only applied to the end points of the members. You will never have a load acting on the middle of a member in a bridge. That is just not the purpose of a bridge. So the weight will always be on the deck, on top of the deck, or somewhere here, but it will never be on one of the members. So another key thing about these trusses that we're dealing with is that they all have their plane in the same dimension. So they're called planar trusses. The beauty of being able to analyze these bridges based off their plane is that we can describe them in a two-dimensional way. So literally as if this was a flat screen and a flat piece of paper, and you can just draw your free body diagram based off of this image here, length and height, length, width, and height. Have you seen the Truss Bridge today? This is an M&M bridge. Why? Because it looks like it has M&Ms in it. I know, it's like, well, bridges.